turning on streaming a little bit early. And this is also why the real-time clocking is useful, because this way I can start streaming early or on time. As long as you know what the exact time mark is, I can do it. The exam is going to be about 1/3 through the semester. So I haven't decided on the exact day yet. Yes, I I heard someone asking questions, but it was really faint. Oh, okay. So let me go unmute myself.
I think that's fine.
There we go. So I should be unmuted over on Google Meet now. All right, cool. Yeah, so the first exam is going to be in week 6, which means in week 5 or so we'll have a practice test. The practice test doesn't really count. I'm only giving you guys the same. I'll give you exam 1 from last semester as a practice. So we'll be working on it together in class. If someone remind me to post it early, I can usually post it too, so that you guys can study with the exam from last semester. I really don't know what a study guide is, because as a college student, I never used one, never had one, have never seen one. So what I'll do is I usually just kind of go over an exam from a past semester. And basically, it's just all the material that we have learned up to this point. So I'm not really sure, what to do with the study guide. And because each semester I try my best to ask new questions. So it's not like we just practice on a whole bunch of questions and expect the same kind of question in our own exam. Oh, okay. Well, I'm glad someone finds old exams to be useful. And if you dig up the YouTube stuff, from the past, I always review exams, especially the first and the second exam. The final exam, sometimes the review is not on YouTube, because that's at the end of the semester. But when it is the first or the second exam, it's always reviewed, and you can always download and watch those YouTube sessions. And no, I do not have links to those specific days, so you're gonna have to dig through my videos from the past. Kind of boils down to the fact that when I was a student, there was no YouTube. YouTube did not exist back then, right? So the question is, how did I study? How did I prepare for my exams when I was a when I was an undergrad student? And that was a long time ago. That was in the late 80s, the mid to late 80s. We didn't have tablets, we didn't have laptop computers. We had dumb terminals. We have hardwired dumb terminals, at the school. So if you want to do the homework assignment, you have to be in the computer lab at school. So if COVID-19 were to happen in that during that time, there will be no homework assignment done. No, I barely escaped punch cards. There were still mainframe computers, so we still had to write programs, submit a job, and then collect the printout on the next day. But I personally did not use any punch cards. We are going to go over binary comparison today, but the lab is going to be on exponential math, basically. So it's a preparation for floating point numbers. So we'll see how far we can go. I'm hoping that I can get into um, a little bit of the math involved, but it's really not something that you have not learned from your algebra classes. Minuend minus subtrahend is difference, yes. And then dividend divided by divisor is the quotient with a remainder. So those terms are really quite useful in computer science, because otherwise we'll just say this number divided by that number, and then this number is the quotient, and then that number is the remainder, and then we have no idea which one we are talking about, right? All right, so I'm gonna get started with the lecture now. All right. So I did rewrite a portion of this module, which is about binary number comparison. So for the most part, comparison is really just subtraction. Okay, we are using subtraction to also perform comparison. So I know it sounds confusing and sounds like, how are those two things related? But we'll see. Okay, we'll get to that point and then we'll see how they are related. So the first thing we want to do is in section 2, because we have all kinds of comparison operators, right? So we got less than, greater than, less than or equal to, greater than or equal to, not equal to, and then equal to. And okay, I barely hear a question. So is someone trying to ask a question? Maybe not. Okay. So so the idea is, inside a processor, do we actually need the transistors to implement every single one of these comparison operators that we are familiar with? And the answer is no. Okay, because we already have Boolean operators, we can do and or, and also negation not. So as a result, all we really need is just being able to tell whether a number is less than another number. That is all that we need. And this little list here is to give you an idea of how we can translate everything, all of the other comparison operators, into just confirming whether something is less than another number or not. All right, so now we can see that we have x is less than y if and only if x is less than y. That one doesn't need any explanation, right? Because all we want to know is whether x is less than y. The second one is, how can we translate greater than into less than? Well, that's pretty easy, right? I mean, all we have to do is to flip the order. And so, if originally we want to confirm whether x is greater than y, we can always just ask the alternative question, which is y less than x? Okay, that's pretty easy to do. The next one is less than or equal to. If we want to confirm whether x is less than or equal to y, instead, we can always try to confirm whether it is not the case that whether y is less than x. The next one is x greater than or equal to y? Closely related to the case above, we just have to flip the positions of x and y, and there we have it. And then we have x does not equal to y. We want to confirm whether x and y are different. And to confirm that, all we have to say is x less than y or y is less than x? Because if one is true, that means x and y are not the same. And then last, we have x equals to y. And being lazy as I am, I just have to say, oh, it's the negation of the one above, because the one above confirms whether x and y are different. So if they are not different, they must be the same. So I just put a big old not logical negation on top of the expression from above, and that's it. Because the point is not to give you the simplest logic to do it. The point is simply to state that it can be done. So the conclusion of section 2 is simply to say, oh, so with all of these comparison operators, all we really need is just to see whether something is less than another something or not. Okay, so that's pretty easy. Okay. Do we have any questions about section 2? No questions? All right. So if there are no questions, yeah, go ahead.
The double arrows mean if and only if, right?
Yes, the double arrow means if and only if, otherwise known as IFF as an abbreviation. And Caleb is also typing, so I'm going to wait a little bit. Is there a specific reason why we use less than instead of greater than for all of these? The answer is yes. Indeed, there's an answer to that one, because we have the borrow. We already know how to compute t of n, where n is the number of bits in the subtractor. We already have t of n, which automatically answers one of the questions down below in section 3. So I'm guessing that is the reason why we have we only confirm whether something is less than something else. So that's a good question because I had to think about it just for a few seconds. I like that. Cool.
Can you show
Go ahead.
can you show an example of the last two?
Can I show an example
Not
of
equal to and equal to.
not equal to?
Can you do that real quick? Yeah.
Okay, so if x and y are different, then one has to be less than the other one. So what I did not say is x and y are integers, either signed or unsigned. But in either case, if x does not equal to y, then one has to be less than the other one.
Right. I guess I'm a little confused of how the or is used.
How the or is used? You mean the plus?
Yes.
Yeah, the plus symbol is borrowed to mean disjunction in this expression. So this is just expressing or, not it is not an actual arithmetic plus.
So if they were not equal to, would they result in like a one or a zero or something? I'm a little confused of how the result would come out.
Okay, so let's just say that x is 2 and y is 3.
Right.
So if x is 2, y is 3, then x is less than y is true. Y is less than x is not true, but then you still have true or false, which is true.
Okay. Right.
And then the other way around is kind of the same because it is symmetric.
Okay. Got it.
Yep. Okay, cool. Any other questions about section 2? All right. So if there are no questions, again, we're going to move on to section 3, which I redid a little bit. So for those of you who downloaded this module and had it printed out or stored in a folder, you might want to download again, because I did some modification. I changed it a little bit. So the first thing we want to confirm is everyone convinced that 0 is less than 1 is true, and then 1 is less than 0 is false? I'm only focused on zeros and ones because, well, we are dealing with binary numbers. Okay, we can only have one of these two values as a single digit. All right, cool. Yeah, we are pretty sure about that. All right, so now we have a small theorem that we want to prove. So the small theorem that we want to prove is presented here. Okay, for any n, 2 to the power of n is greater than the sigma or summation, where I goes from 0 to n minus 1, and then the term that we are actually adding is 2 to the power of I. So that's a fancy way to basically say, if n is 3, okay, 2 to the power of 3 is greater than 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0. Now, whether we want to start with 0 or not really doesn't matter because we can start with a negative integer. So anything that is fractional can also be added. In other words, if you just add up all the smaller powers of 2, it will never be equal to or greater than, 2 to the power of n. That's basically what this little theorem is saying. Which seems to make sense, right? Because 8 is greater than 4 plus 2 plus 1, and if you want to add halves, quarters, eighths, sixteenths, and so on, it will still be greater than that. And it doesn't matter what n is. Okay, so it seems to make sense to us. But how do you know that is actually true? Okay, so a lot of times, especially in computer science, there's a general attitude of, okay, this works, so, and this works, and this works, so I'm going to generalize that this whole thing, substituting constants with variables is going to work in general. A lot of times that works, but sometimes it doesn't work. It is that sometimes when it doesn't work, that is going to cost us big time. So we really want to be able to prove these things, claims like what I'm talking about here, using rigid mathematical proof. And somebody's going to point out and go like, but that's CISP 440 stuff. It is not CISP 310 stuff. That is why okay, let me backtrack a little bit. Somebody asked me, since I'm teaching 310 and 440 every semester, this is actually a counselor asked, um, whether they should recommend students to take both classes in the same semester or not. And the answer was, my answer was, it depends on how the student look at things. Because if a student look at things, with compartmentalizing each class by itself, then it is a heavy load. Okay, 310, there's a lot of stuff, new concept. It relates to CISP 360, but not really all that much. 440 is in a way worse, right? Because it's basically a math class and using computer science as an excuse to introduce those topics. So those two classes tend to be difficult. However, I told the counselor, if a student can relate the material from CISP 310 and the material in CISP 440 and also the material from all the other classes that the student had taken already, then it really is boiling down to one class and a half. Okay, in other words, the effort to succeed in both classes is actually less than having to take two classes, in the full. And that is why I like to introduce concepts like these in my CISP 310 class. Because if you have not taken CISP 440, it gives you an exposure to proof by induction. If you have taken CISP 440, it is a review. Either way, you are getting it's not time wasted. I'll put it that way. Okay, so I'm not going to go through the entire proof. Okay, you guys can spend the time to read the entire proof. But the bottom line is we can indeed prove that this is true for all non-negative integers of n. Well, actually, I take it back. If you start I from a negative infinity value, n can be a negative integer, and it still works. We have Nicholas typing something, so I'm going to wait a little bit. The sigma is, yes, so you have an example to illustrate what the theorem is trying to say. That is correct. That is correct. So the example that you're giving, Nicholas, is a validation or is a confirmation that at least for one case, the theorem is true. But the question is, how do you know it is true in general? In other words, if n is 100, are we going to test all the cases, where, yeah, so the question is, do you need to use actual numerical value to verify, or do we want to use a theorem to basically say, yep, it is true for all n? But it is a good example. What Nicholas has typed in the text channel is an example of what the theorem is trying to illustrate. Cool. So what we have next, but this has nothing, well, it seems to have nothing to do with binary comparison. So what we want to do now is to focus on this part here. I changed my mouse pointer, by the way, because the other one is a little bit too big and it interferes with how I would like to navigate and hover over, in Logisim. So I changed my mouse pointer. This is called a dot mouse pointer in Linux. You can actually download the theme if you're using Linux and change it too. It's kind of cool. All right, so getting back to where we are. So now if we want to prove an m-bit subtraction in an m-bit subtraction, U of m is the unsigned interpretation of m bits of x, which is a bit pattern. If we want to confirm whether the value, the unsigned interpretation of the bit pattern x, is less than the unsigned interpretation of the bit pattern y, all we need is to take a look at Tm and see whether it is 1. Tm is 1 if and only if x is less than y. I know, there's a whole bunch of there are some phrases that I have simplified. Instead of saying, the m-bit unsigned interpretation of y is less than the m-bit unsigned interpretation of y. So I'm just saying that x is less than y for the most part. All right. And what is T of m? What do you think is T of M? We have introduced T of something in prior classes, and it is coming back to show us how useful it is. It is
The remainder?
no. T is from take away, right? From taking. So it is basically the borrow. But I didn't want to use B because B is the name of the function already. So I use the T row instead of the C row for the K row for adding. It is the T row for subtracting. So T of M is the borrow from bit M in the subtraction. So this statement is saying if we only focus on M bits, okay, whether a bit pattern is less than another bit pattern interpreted unsigned, we can just look at the T bit. Okay, the overall T bit will tell us. If the overall T bit is a 1, it means x is less than y. If the overall T bit is a 0, it means x is not less than y. Now remember, if x is not less than y, it doesn't automatically say x is greater than y. All it says is x is not less than y, which means they can be equal or x can be greater than y. So do we have any questions up to this point? Oh, I made a mistake here, didn't I? Because I shouldn't have used k of 0. I should have used t of 0. Darn it, I knew I always miss something because I just worked on this today and then I missed it. Okay, fine, I'll fix it. Okay, so I just have to look for k0, which appeared only once. Change that to t of 0, and then we publish. And we are here to refresh it, and it should be done. Alright, so getting back to where we were. Yep, got it fixed right here. So do we have any questions about what this statement is saying? Because the rest is the proof of this. Okay, but if we don't know what theorem we are trying to prove, then we are in big trouble, right? So we have to make sure that we understand what the theorem is really trying to say first. So I'm looking at the text channel. Andrew says, T of M is whether the borrow flag is on or not. That is correct. It's the overall borrow. It's the overall borrow from a M bit subtraction. And then Victor said, so if there's an overall borrow, that means x is less than y. To be more specific, I know Victor has the right idea, but I just want to be more specific. So if the overall borrow is a 1, it means x is less than y. Yes, the borrow means it's overall borrow, but that's why I use TM, because TM is very specific about which borrow we are talking about. It is the borrow in column M. So that makes it super specific. All right, so next question is coming from Omar. Oh, no, it's coming from Zoe. The borrow means there's an overflow. No. So borrow and overflow are they're not entirely different. They do have some correlation, but they are not the same thing. Definitely not the same thing. The borrow is the one that is defined here. Okay, so if you follow my mouse pointer, this is how we define the T or the borrow flag at position I plus 1. And then Omar is saying, so we are comparing bit M of unsigned binary numbers x and y. We are trying to figure out whether x as an m-bit number is less than y as an m-bit number, and we are trying to rely on we're trying to only rely on T of M, which is the overall borrow after a subtraction. And the subtraction is always x minus y. X is the minuend and y is the subtrahend. All right, we got some more questions. M is not the base. M is the number of bits in the subtraction, in the binary subtraction. So m is not the base. We are only dealing with base 2 in this case. All right. All right, so Victor says, so m is always going to be the number of bits plus 1. No, m is the number of bits. Remember, when we have m bits, the position of the bits goes from 0 to m minus 1 because it is always 0 oriented. And then Andrew asked, what happens when both numbers have the same MSB? Does the algorithm recompare the next bit? Aha! Okay, so I will answer that question in just a little bit. And then Nathan asked, is m the place of the most significant bit? The answer is no. M is the number of bits. The place of the most significant bit is m minus 1 because we count from 0. Alright, so maybe we need an example. I'm just guessing. So we'll use an example. I'm setting up the tablet right now. Okay, so we got that up and running. And I'm just looking to see if I already have one of the sessions running, and I do not. I'm going to start one from the command line right now. And I think I have to do it twice. The first time I start it, it doesn't actually refresh, and then I have to do it again. Let me see if that's true. Yep. Don't know exactly why. The first time I do this, it doesn't actually do it, and then I have to do it one more time. Then it works. Nope. Nope. Okay. I just typed the wrong key. There we go. Okay. So now let me resize it and put it into the part that you guys can all see. There we go. Yeah, examples are great. There we go. And we can make it slightly bigger. I kind of like my mouse pointer. It looks kind of cool. All right. So let's go ahead and say m equals to 4. In other words, we are performing 4-bit subtractions. So when we're dealing with 4-bit subtractions, we'll use concrete numbers, okay? So let's say we have 1010 minus 1011 in base 2. So these are all in base 2. So we got x as our minuend, we got y as our subtrahend. This row is called q, and then this row is t, and then this row is d, which is our difference. So x minus 0 minus 1 is a 1 with a borrow of 1. And we are assuming t0 is a 0, so we always put a 0 here. So 1 minus 0 is a 1. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow of 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with an overall borrow. And then 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. So now we look at the bit positions. This is bit position 0, bit position 1, bit position 2, bit position 3, and this is bit position 4. So T4 is referring to this one here. This is our T4. And the claim in my notes is basically saying in the case of a 4-bit subtraction, T4 alone is enough to tell us whether x is less than y if we choose to interpret x and y as unsigned values. Okay, so now is a good time to also introduce the u notation. So the u notation, in this case u4 of x, is basically the unsigned for the 4-bit unsigned interpretation of the bit pattern x. Now x is 1010, so that will make the unsigned interpretation to be what we know as 10 in base 10. So I'm going to emphasize this is in base 10 by writing it in subscript 10. What about the other one? So the other one, u4 of y, y is 1011. So the unsigned 4-bit interpretation of y is going to be 11 in base 10. Yeah, I think I chose poorly because 10 looks like 1 0 in base 2, and then 11 looks like 1 1 in base 2, and that's why I emphasize that, this is actually 10 in base 10, and this is actually, 11 in base 10. So is that okay? This is a confirmation, right? This is a confirmation that, hey, that seems to work. So let's look at another example, okay? Also with 4 bits. So we have 0, 1, 1, 0 minus 0, 1, 1, 0. I don't think this one, really needs to be explained a whole lot, right? I think everybody can be convinced that the result is all zeros with a overall borrow of also 0, right? So this overall borrow of 0 is telling us that 0, 1, 1, 0 in base 2 is not less than 0, 1, 1, 0 in base 2 if we choose to interpret 0, 1, 1, 0 as a 4-bit unsigned number. That's all the theorem is saying. Are we good so far? Cool, cool. And I'll give you guys one more example, okay? And this one looks really kind of odd because, it is really obvious, okay? Tech, why do you even bother with this example, okay? But there's a reason why I'm going to go through this example. So I'm going to use 1, 1, 1, 1 minus 0, 0, 0, 1. This is x, this is y, and you guys look at this and go like, oh, that's easy. We already know the answer. Well, I'm going to work out the entire thing, and then just so that, we know how to do this, okay? So 1 minus 1 is a 0, t0 is assumed to be 0, and then 0 minus 0 is 0 over here. And because neither subtraction is giving me a borrow of 1, so the borrow is going to be a 0 in bit position 1. So 1 minus 0 is a 1, 1 minus 0 is a 1, no borrow from the next column. 1 minus 0 is a 1, 1 minus 0 is a 1, no borrow from the next column. 1 minus 0 is a 1, 1 minus 0 is a 1, no borrow from the next column. So in this particular one, we can also see that the borrow flag of B4, or T4, excuse me, T4 is a 0, which is telling us the unsigned interpretation of the 4-bit bit pattern 1111 is not less than the unsigned 4-bit interpretation of 0001. Okay, and that's hardly surprising because the 4-bit unsigned interpretation of x in this case is 15 in base 10, and the other one, I mean, this one I don't think I need to explain it too much. It's just 1 in whatever base, right? So it looks like, yeah, we got this down. Okay, it's okay. We got it. Okay. So the next question is, but how do we know this will continue to work when we deal with 32-bit numbers, 64-bit numbers, 128-bit numbers, and so on? Just because it works in 4-bit doesn't mean it's going to work in other widths, of integers. And that's basically what the proof is about. Okay, it is basically proving once and for all that we can always rely on the overall borrow in a binary subtraction, and it can always reliably tell us whether the minuend is less than the subtrahend if we choose to interpret the values as unsigned. Okay, so I'm not gonna go through the proofs. Okay, if somebody is interested, please go ahead and read the proof. Okay, I did spend the time to write it. But if you're not interested in the proof, I can tell you that the exam is not gonna rely on the proof. Okay, so you don't have to know how to do this proof. But if you say, hey, I have taken CISP440, I know what is proof by induction, I want to see how it is applied in this proof, then go ahead and read it. I don't know. I don't know how this topic is treated in CISP 440. It depends on who is teaching and which campus you're taking it from. Because ARC is the math part. It's using the same technique. Proof by induction is a proof technique, and I'm just applying the proof technique to this to the theorem that we are talking about here. And the theorem that we are talking about is really summarized in this one little thing over here. I mean, that's really the bottom line of what we are trying to prove. And it is true, okay? Yeah, we can actually prove it. We can rely on just the overall borrow to tell us whether the minuend is less than the subtrahend after a binary subtraction. All right, so we got Keaton typing up. I would say yes, Luke. Oh, okay. I'm glad someone is remembering, certain techniques from another class. Um, so in CISP310, we focus on the result because we're only trying to use the result, which is this theorem. So we are not focusing on the proof itself. CISP440, on the other hand, is going to focus on more on the proof, because that's the technique that people need to learn in CISP440. So J is going to be encountering proof by induction and also proof by contradiction too. Those are the two really powerful proof techniques in computer science. All right. So I'm not going to go through the proof, which means we are skipping a big O section, okay? So now we move on to signed interpretation. Signed interpretation is based on 2's complement that we talked about the other day. So instead of using 2's complement, there's another way to find out what value is being represented by a bit pattern. So once again, we have a bit pattern that is only m bit wide. The bit pattern itself is x. So the question is, what is the signed interpretation of m bits in x? Okay, that's the question. And you can see this is not relying on 2's complement because it does in a way, but it doesn't in another way. So this part here, okay, this part here is using 2's complement, and this part here is not using 2's complement. And the reason why we have something like this has to do with we are looking at the sign bit. Okay, x subscript m minus 1 is the most significant bit, which is also called the sign bit. If the sign bit is a 1, then we use this formula to figure out what value is being represented. We're basically performing 2's complement in the inside and then do an arithmetic negation on the outside so we can actually get to. So the inside portion gets to the absolute value, and then the outside minus the negation, arithmetic negation, is flipping the sign of the absolute value, so we end up with a negative value. If the most significant bit is a 0, then all we do is to add up all the bits, including the most significant bit. But in this case, it's okay to add up the most significant bit because the most significant bit is already known to be a 0, so it's not going to contribute to the sigma notation. So the first line of how v of x is defined definitely take into consideration the value of the sign flag, okay, the sign bit, the most significant bit, so that we utilize one formula in the case that the sign bit is a 1, and then we use another formula when the sign bit is a 0 in order to figure out what value is being represented. But through some algebra tricks and magic, they actually turn out to be the same thing. Okay? In other words, regardless of what the sign bit value is, we can always just use this one single formula to find out what signed value is being represented by a bit pattern. So you look at this particular equation or formula and you go like, well, that looks really confusing. What does it mean, right? So the first thing we have to pay attention to is the sigma doesn't go from 0 to m minus 1 anymore. It only goes from 0 to m minus 2 in this case. So the most significant bit is not taken into consideration in the sigma. So the sigma is adding up the 2's power and the digit at each position all the way up to and excluding the most significant bit. The most significant bit, which is x m minus 1, is used to determine whether we need to subtract 2 to the power of m minus 1 from the sigma or not. Okay, so what does that mean? Give us an example, right? Okay, so I'll give you examples. So getting back to the tablet. So the first example I'm going to use is 1111. Okay, so we say x equals to 1111. What is v of x? Okay, so using the formula, okay, switching back to here, we are basically adding, we are multiplying each digit to its corresponding power of 2 for the least significant 3 bits. And then the most significant bit is going to determine whether we have to subtract 2 to the power of 3 from the sum or not. Okay, so getting back to 1111. Okay, so x is 1111. V of x is going to be 1 plus 2 plus 4 minus 8. And that turns out to be negative 1. Is that okay? Is everybody connecting the actual equation to the example that we are talking about here? We can try another one. So we can try 1010. Okay, so 1010 in base 2 is going to be 0. There's 0 of 1, 1 of 2, none of 4, and we have to subtract the 8 because the most significant bit is 1. So we have 2 minus 8, which is negative 6. So the question is it really representing negative 6? So a quick way to check this is to draw a half circle because I don't want to use the time to draw a full circle, so we are drawing a half circle this time. So we chop it up to the number of sections that we need in this case. This is going to be 0. Okay, this is 0, 0, 0, 0, 0. Oops. This is 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1. Then we have 1, 0, 1, 0. Okay, that's all we need. Alright, so this is representing 0 all the way here. This is representing negative 1, negative 2, negative 3, negative 4, negative 5, and magically negative 6. Voila. Isn't that cool? So the equation of v is really just a handy way to find out if I want to look at a bit pattern as a signed, using the signed interpretation, what value is it representing? And it's almost exactly the same as an unsigned number, except instead of adding the power of 2 corresponding to the most significant bit, we are subtracting it. That's all. That is the only difference. All right? So are we good so far about what the v function is about? Let me switch back to the notes so that you can see the v function. So v of x is this sigma minus this term. All right, excellent. So now the question is, so then how is this helping us to find out whether x is less than y in a subtraction? But this time we want to use the signed interpretation. And somebody's going to say, but we got the borrow already. Aren't we done already in this class? I mean, in this particular module? The answer is no. Okay, so we're going to switch back to the notes a little bit, and we'll look at an example that we have done already. We'll look at this particular example. Okay, and we use this to determine that x, if we want to look at the bit pattern x and choose to use the signed interpretation, x is representing negative 1. Y is representing 1, right? So now the question is, well, is negative 1 less than 1? The answer is yes, it is. It's supposed to be, right? Negative 1 is less than 1. But if we look at T4, T4 is saying nope. And that is because T4 is only useful when we want to use the unsigned interpretation. Because the unsigned interpretation of 1111 in base 2 is the value of 15. But the signed interpretation of 1111 is the value of negative 1. and this is why we cannot use the overall borrow after a subtraction to figure out whether x is less than y or not. Sometimes it works, sometimes it doesn't work. Okay, sometimes the overall borrow, even when applied to signed interpretation, will still work, but it doesn't work all the time, which is the problem. So now we look at this problem and go like, darn it, so what are we going to do? So what we're going to do is to work out some really simple inequality stuff. Okay, this is the part that I'm talking about here. Okay, so we say, well, if x is less than y, if and only if x minus y is less than y minus y, right? Because remember, inequality, is similar to equality in many ways. If you remove the same amount from both sides, the inequality should still hold, right? So the first line leading to the second line is kind of okay. What is the big deal? Well, the big deal is if you subtract y from y, you get 0. So all we are really asking is whether x minus y is less than 0. X minus y, by the way, is d, right? D is the difference. So all we are really asking is whether the difference is less than 0 or not. And most of you have, already reviewed the material, and you already know that, oh, so this is an easy question then, because we can always tell whether the difference is less than 0 or not by looking at the sign bit, or the most significant bit of the difference. Done, right? Well, unfortunately, no. We're not quite done yet. Okay, so I'll give you a few examples where it works, and then I'll give you an example where it doesn't work. There are a few examples here in the notes. Okay, and it's kind of an exercise for you guys to try out. Okay, so I'll pick a few to try out, and then we'll just to get to the point of oh, so this is not working, right? Okay, so we'll try out the first one. Okay, 6 minus 3, and we'll go ahead and use the tablet to figure out what is 6 minus 3 in binary subtraction, and then we'll see how the sign flag is working in this case. So let me turn on the tablet again, switch to a new page, and then we have 6 minus 3. 6 is 0, 1, 1, 0, and then 3 is 0, 0, 1, 1 in base 2. So these are all in base 2. 0 minus 1 is a 1 with a borrow, and 1 minus 0 is a 1. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow. 1 minus 0 is a 1. 1 minus 1 is a 0. Neither has an overall borrow, so we have a borrow of 0 here. 0 minus 0 is a 0. 0 minus 0 is a 0 with no overall borrow over here. Okay, so done, right? But remember, this time we are focusing on the signed interpretation, which means we are not even going to pay attention to the overall borrow. Okay, so this bit is completely ignored in this case because we are not interpreting the bit pattern as unsigned, so we don't pay attention to the overall borrow at all. So instead, we are paying attention to the sign bit of the difference. Okay, the sign bit of the difference is a 0, which means x minus y is non-negative, which then implies x is not less than y. Yes. So to answer Sun Jules' question, 1, 0, 0, 0 in base 2 can be interpreted as -8 if we choose the assigned interpretation. Alright, but getting back to the tablet. So this is telling us that v, which is the signed interpretation of 0, 1, 1, 0, is less than the v of 0, 0, 1, 1 is false, which means it is greater than or equal to, which works out, right? This is cool. Then somebody's going to say, maybe this is because the both minuend and subtrahend are non-negative. Okay, this is the reason why it works. Nope, I can give you some other examples. Okay, so switching back to the notes, Let us pick the second one. Okay, the second one is -1 minus -2. Okay, so we'll try that out. So -1 is 1, 1, 1, 1. -2 is 1, 1, 1, 0. Okay, this is a very easy subtraction, right? But we'll go through the full motion of the binary subtraction. 1 minus 0 is a 1. 1 minus 0 is a 1. No overall borrow of 1. 1 minus 1 is a 0. 0 minus 0 is a 0. No overall borrow of 1. 1 minus 1 is a 0. 0 minus 0 is a 0. Same thing. No overall borrow. 1 minus 1 is a 0. 0 minus 0 is a 0. And no overall borrow. Once again, we ignore this one. And we take this one and go like, oh, okay. So the signed interpretation of 1, 1, 1, 1 is less than the signed interpretation of 1, 1, 1, 0 is false, which is great. Okay, this works because -1 is less than -2 is false. Okay, it works. So in the text channel we have no. No, that is the whole point I'm trying to say. It is not the case. We're getting to the example where this doesn't work anymore. The whole idea is don't look at the borrow if we are interpreting as signed values. Okay, I think I've said that many times. Okay, if it is signed, don't look at the borrow. Okay, so getting back to the example. Okay, so I need to show you guys how this is not gonna work, right? So we'll try -4 minus -5. Excuse me, -4 minus 5. Okay, so -4 is 1, 1, 0, 0, and then 5 is 0, 1, 0, 1. So we'll do the subtraction. 0 minus 1 is a 1 with a borrow of 1. 1 minus 0 is a 1. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow of 1. 1 minus 1 is a 0. 0 minus 1 is a 1 with a borrow of 1. 1 minus 0 is a 1. 1 minus 1 is a 0. And there's no overall borrow of anything. Okay. So this time, once again, we ignore the borrow flag. Okay. Because the borrow flag is useless. Okay. If you want to use the signed interpretation, the borrow flag is useless. And we look at the sign flag, right? The sign flag says, okay, the signed value represented by 1, 1, 0, 0 is less than the signed value represented by 0, 1, 0, 1 is false. Wait, hold on a second here. This makes no sense, right? Because we have -4 being represented by 1, 1, 0, 0, and then we have 5 being represented by 0, 1, 0, 1. What do you mean by -4 is not less than 5? Oops, looks like we have a little bit of a problem. Okay, so I'll show you yet another example, and then we'll kind of go take a look at what went wrong and how we're going to fix it. Okay, so and then Tigran has or Tigran, I don't know exactly the pronunciation. So says if signed borrow does not, we just don't pay attention to it. It is still there. We just don't look at it. Okay, we don't use it to tell us whether x is less than y. We just ignore. All right. So now we look at another example. So the last example is 6 minus -5. Well, both of these will work. Let me see. 5 minus -4. Okay, let's do 5 minus -4 because it's just the reverse of what we just did, right? So that will be easy. 0, 1, 0, 1 minus 1, 1, 0, 0. So now we figure this out. 1 minus 0 is a 1. 1 minus 0 is a 1. There's no borrow from the next column. 0 minus 0 is a 0. 0 minus 0 is a 0. No borrow from the next column. 1 minus 1 is a 0. 0 minus 0 is a 0. No borrow from the next column. 0 minus 1 is a 1 with a borrow. and borrow of 1. 1 minus 0 is a 1. Once again, ignore this one. Pay attention to this one. Okay? So this one is telling us the signed value represented by 0101 is less than the signed value represented by 1100 is true. Wait, that doesn't make any sense, does it? Right? Because this is 5, this is negative 4. 5 is less than negative 4 is true. What? It doesn't work, right? So why does it work sometimes? Like these two cases, it works. Okay, with these two cases it works. With these two cases, it doesn't work. The reason has to do with the difference. Okay, because when you look at the difference, negative 4 minus 5, this is 7. That makes no sense, right? Negative 4 minus 5 is not 7. I mean, if you subtract a non-negative value from a negative value, you should stay on the negative side. So ignoring the actual value of 7, the sign itself is wrong. Okay? And that's why we came to the wrong conclusion. Okay, the other one. 5 minus negative 4 is supposed to be 9. But when we look at the actual result of the subtraction, I think this is negative 7. Okay? That makes no sense either, right? Because when you subtract a negative quantity from a non-negative quantity, the difference should stay non-negative. And yet we have the wrong sign. Regardless of how wrong it is on the negative side, the sign itself is wrong. So this has to do with overflow. Okay? Remember the overflow flag of the lab on Tuesday? This is the reason why it doesn't work, and it is also the reason why overflow is important. Okay, so Omar has gotten it. Okay, Omar just typed it probably right before I said it. Yep, that's it. That's it. Okay, it is because of overflow. Oh, right after? Okay. You probably started typing as I was talking. Yep, and then there's the lag time involved too. Yep, it's okay. It's not Jeopardy. Because in the Jeopardy, then actually Omar has gotten it right too. That answer would have worked in Jeopardy because it is in the form of a question. Good job. So let's check out the overflow, okay? Because let's see what the overflow is for all 4 cases, okay? So the overflow takes a look at the sign of the minuend, the sign of the subtrahend, and also the sign of the difference. Okay, basically, if the sign of the minuend is opposite to the signs of the subtrahend and also the difference, then we have an overflow. And then Alexander is asking, can we just say T or F true or false by comparing numbers without any calculations? I'm not really quite sure what that is asking. How do we get to the sign flag if we don't actually do the calculations? That's my question to your question. Is if we don't do any calculations, how do we get to the sign flags? So I don't think there's a way to get to I don't think there's a way to confirm, whether the less than is true or not without the actual subtraction. All right. Okay, so I thought somebody else was typing too, but since there's nothing coming out of the text channel, I'm not gonna hold on to that. If you guys have any questions, go ahead and type it in, and then I'm gonna work out the overflow flag for all 4 of these cases. Okay, so for the first one, we have basically I'm gonna use a circle, okay, to indicate what we pay attention to. So in this case, the sign flag of the minuend is not the opposite of both the subtrahend and the difference, so the overflow is a 0 in this case. So I put a stroke, when we have both in the same equation. In this case, definitely not opposite, because when the signs of the minuet and the subtrahend are the same, we're definitely not going to have an overflow of 1. So overflow is a 0 in this case as well. And then over here, we take a look, and this one is going to have overflow being a 1, because the sign of the minuend is opposite to the signs of the subtrahend and the difference. And over here, same situation, it is opposite. So we have overflow being a 1 in this case as well. Okay, I think we're seeing a pattern here. Okay, the pattern is if overflow is a 0, then we can trust the sign flag. The sign flag is reliable. If the overflow is a 1, then the sign flag is saying exactly the opposite. Okay, that seems to be the case, right? Just looking at these 4 examples, it seems to be the case that when overflow is a 0, we can trust the sign flag to indicate whether x is less than y after a subtraction. And when the overflow is a 1, then the sign flag is going to say exactly the opposite to the correct answer. Okay, so I just want to pause here to make sure everybody is getting this point. And we got a whole bunch of people typing, so this is good. Okay, this is what I'm waiting for, is for people to type the questions, because this tells me that people are paying attention, they're thinking. All right, so the first question is, so we can only determine overflow after we have found the MSB of the difference. That is correct. So Nathan is correct about that. So let me use my latest Discord foo to reply to that. Okay, and then we got a few more people typing too, so give me a chance to practice my Discord foo. Alright, so next question up. Okay, this time I'm gonna add a reaction to it. There we go. And all without really using the mouse too. Yes, I'm pretty proud of myself learning how to do things in Discord without having to use the mouse. No, it is not Discord Vim. It is if you type // in Discord, it will show you the shortcut keys. Yeah, the plus emote works only for the last message. If you are a few messages back, it doesn't work. Okay, let me show you which one doesn't work. Like Omar's message, which is like a few messages back, the plus doesn't work because the plus only would add a reaction to the latest one. So to add, but I can do this, without touching the mouse because I got a few things going for me. But even without the macro key expansion thing, I can still do it without the mouse. It's just a little bit more typing in that case. All right, moving on to Keaton. What do you mean by exact opposite? It means if one is 0, the other two should be 1s. If the first one is a 1, the other two should be 0s. Oh, Vim is the editor, Jonathan. Vim is the editor to learn. And Jackie is correct. Jackie's interpretation of what I said opposite is correct. If the minuend has a value of 0 as its most significant bit, then the other two should be 1s. If the MSB of the minuend is a 1, then the other two should be 0s. That is correct. Okay, so Darvish said, is there any way to derive the logic for overflow from the two subtractions that I did? Well, the overflow logic is already done in the lab. It's basically saying the sign doesn't make sense. The sign of the difference does not make sense. That is how the overflow equation is derived. Emax. Emax also stands for memory pig. Okay. Friends for garbage. I guess memory pig works too. If overflow is true, what do you do with the result you come up with? Okay, that's the next question. So Nathan C's question, it will be answered in just a little bit. I think we have 3 Nathans in this class. And then Darvish said, honestly, I told Vim, but I'm still lazy for most stuff and use VS Code. Autocomplete. I mean, who needs autocomplete? No, Zoe, that is not the case. Okay, borrow and overflow do not mix. Sign and overflow mix, but not borrow. We simply ignore borrow whenever we choose to interpret using the signed interpretation. All right. Yeah, 32 gigs of RAM goes away just like that. It's in my case, the browser just chews up RAM. There's no tomorrow. Alrighty. So it looks like we got all the concept stuff done. That is correct. Luke is correct. We do ignore overflow when we use the unsigned interpretation. That is correct. Alright, so we got a few more people typing. Yes. Chrome, Firefox, they all chew up memory. Well, using Linux helps a little bit, but doesn't help that much when we have a lot of browser stuff going on. Alright, so I'm going to assume that we are done with on-topic stuff. Alright, so there's one on-topic question. When overflow is 1, can we set up opposite of sign being true or false? Yes, that's what we want to do. And I'm going to show you guys how to do it. And you guys will go like, really? It's that thing again? Yes, it is that thing again. Yeah, I tried that too. Brave. Okay, I'm just trying to see if there are any more on-topic stuff. Looks like we are done with the on-topic stuff. That's why we have the off-topic text channel. But I suppose I'm the first one who started in the off-topic stuff by saying, by mentioning all the Discord foo stuff. So that is definitely my fault. All right. So now we want to look at the next slide where we say there's a column for sign, there's a column for O, and there's a column of is x less than y. Okay, so this is again the truth table. It's a pretty simple truth table. There are only 4 rows involved here because sign is a Boolean. So sign itself can be false or true. When sign is false, overflow, okay, put a stroke across the 0 in this case because this is overflow O. So when the sign is a 0, overflow can be a 0 or 1. When the sign is a 1, overflow can also be a 0 or 1. So now the question is, so what is the conclusion, right? What is the conclusion whether x is less than y or not? Okay. So remember what I said? When the overflow is a 0, we can trust the sign flag, right? So for these two rows, okay, for this row and this row over here, the first row and the third row, because the overflow flag is a 0, so we can actually trust the sign flag. When the sign flag is a 0, x is less than y is false. And when the sign flag is a 1, x is less than y is true. Okay, those are the two easy ones. And then for row 2 and row 4, the overflow flag is a 1. But remember what I said, when the overflow flag is a 1, it means the sign flag is opposite to what it is supposed to be. So that means on row 2, x is less than y is actually true because the sign flag is saying exactly the opposite of what it is supposed to be. And then on row 4, because the overflow is a 1, it means the sign flag is telling us the exact opposite, and as a result, in this case, x is less than y is false. All right? Okay. So now we asked the question, if we want to name this column L for less than, how would we compute L from the sign flag and the overflow flag? So here's the question, and this is an operator that we have seen before, and it's coming back and say, hey, I'm actually useful here too. Yep, you guys are all correct. It is exclusive OR. Good job. It is indeed exclusive OR. So the L flag, which is the summary, this is the one result that we want. Okay, if you look at the L flag, which is the exclusive OR between the sign and the overflow flag, if this is a 1, if the L flag is a 1, it means using the signed interpretation, x is indeed less than y. If the L flag is a 0, then x is less than y is false. Okay, you're looking at the bit patterns using the signed interpretation. So that's it. Okay, that's basically the whole module. And this is also why we had to pay attention or explain the overflow flag, because the sign flag alone cannot get the job done, but with the help of the overflow flag, then the exclusive OR between those two flags can reliably tell us whether the signed interpretation of x is less than the signed interpretation of y. All right. So yes. So we went around, kind of like we took a scenic route, to get to this point. But I'm hoping, at this point you guys start to see that, oh, so that's why we need the overflow flag. So all of these flags, the borrow flag, the sign flag, the overflow flag, and also the L flag, they are all implemented in hardware. Okay, so we'll get to the point when I explain the inside of the ALU, or the arithmetic and logic unit inside the processor. That's when we will start to actually see the implementation of the logic of these flags. So are we good so far with this module? Are there any additional on-topic questions about the flags? Okay, I'm just scrolling down to see what else is here. Yep, so we got the exclusive OR. That's just the other way to say exclusive OR, the long way of saying that. Yes, Omar is correct. D minus 1, D m minus 1 is indeed the sign flag. When m is the number of bits, then that is the sign flag. So the sign flag, okay, let me type it here. So the sign flag, which is usually abbreviated as S, is indeed D subscript m minus 1 when we are talking about an m bit subtraction. Yes, I have to use MathBot for this. Alright, so I'm looking at the time, and we still got time. Woohoo! Yes. Okay, we got 10 more minutes. So with these 10 minutes, we'll go into scientific notation. Okay, so we'll get to the power stuff. Okay, so let me take a look. Which is also going to be our lab tonight. Yes, I have a lab tonight. I know tomorrow there's no school tomorrow, but we still have a lab tonight. So the floating point number representation is this module, and I have not redone it yet. Okay, so you cannot look at the LaTeX representation just yet with this one. And we have a little bit of an issue here. It's okay, I told I can. Let me see if I can just regen the page at this point, because it depends on which render engine I use. One of the render engines, does not take certain LaTeX expressions, at all. So let me give it a try. And this is module 0296. Alright, so it's regenerating the page. Alright, so Control Shift R. Yeah, see, much better. Fixed the problem. Alright, so the first thing we want to deal with, in today's lab is really just log stuff. Okay, so instead of talking about scientific notation stuff, let me just kind of remind you guys how log work. Okay, log and exponents. Not really a big deal. Okay, and that was pretty good, Aaron. You recognized my daughter. She was just kind of walking behind me. Right, log stuff. There we go. So the log stuff is the log. If you want to use a base for a log of a particular value x, this is really just log. We'll choose another base. This is b1. This is b2. So it's b2 of x, the whole thing divided by log b1 of b2. Okay, I think that is right. Okay, so let me let me check. Yeah, that looks right to me. Alright, so that's one. And then the other one, okay, how about this? We got 7 minutes. Alright, so with 7 minutes, I can actually open the lab, well, actually go through the lab preview first, and then I'll open the lab at the end of the class. I think this is going to be more helpful. Alright, so you cannot open it yet, because I'm just doing a quick preview. Alright, so the first question is, consider the base 10 number is as follows in scientific notation. Alright, so you have to remember what scientific notation looks like in C. So let me just go ahead and give you the syntax of scientific notation. So let's say we have 12.34 E56. Okay, this means the value is 12.34 times 10 to the power of 56. So this E is not the natural log E. It is just an indication, it's just a separator of what we usually call the mantissa from 10th power, from the exponent of 10. So do we have any questions about the scientific notation in C? This is actually this is the syntax in C. This is how we use scientific notation in C, C++. Okay. So we got 2 people typing here, and I'm just gonna wait a little bit. Nope, it is not. So engineering notation, if you're using engineering notation, then we only use steps of 3. So the power of 10 is always a multiple of 3. But this e over here is really just separating the mantissa, which is to its left hand side, from the exponent of 10, which is to the right hand side of the e. So okay, so I'm so glad that I actually went over this part, because otherwise people would have a lot of questions um, in the lab tonight. All right, so with this out of the way, let's go back to the question. So it is conventional to normalize the mantissa so that it's greater than or equal to 1 but less than 10. If we are to normalize the mantissa but maintain the value being represented, what is the new exponent? Okay, in other words, how do we adjust so that this becomes, okay, in this case it becomes 7.32631 e whatever. Okay, what is the new e gonna be? Okay, that's kind of the question. Moving on to question number 2. So question number 2 is, consider the value represented by the following base 10 number. So once again, this is a scientific notation, which means the value being represented is 671 times 10 to the power of 6 in this case. What is the exponent of the largest power of 2 that is less than or equal to this value? In other words, find the largest integer p such that p2 to the power of p is less than or equal to 671 e6. So this is where log can come in handy. But for those of you who absolutely do not want to review your log stuff, you can look at this question and use a spreadsheet to fix the problem too. So within the spreadsheet, just have a column for all the values of p, starting from 1, and then go all the way down, and then in another column, you compute your 2 to the power of the value of the first column, and just keep going until you see something that is greater than 671 E6, and the number right before is going to be the answer. Okay, so I can give the equation. Okay, so don't give the answer out. I can give the general equation. Okay. Okay, so here's the thing. So 2. Okay. I'm not going to use a specific base because that would be giving away too much. So b to the power of p equals to x. And to solve for p, okay, you take the log on both sides, and it doesn't matter what log you're using too in this case. So you can use whatever log, okay, base 10, using the natural log, base 2, whatever. So the log of bp is the log of x, okay? Kind of makes sense, because if bp and x start off to be the same to begin with, when you take the log should also be the same. But the thing about this is you can also, when you have b to the power of p, the power can now go outside and become a multiplier to log of b equals to the log of x. So if b and x are given, you can now solve for p. And yes, I know this is a equation and not an inequality. So, in the case of an inequality, you just have to think about how to convert from a equation to a inequality with the restriction that p has to be an integer. Okay? So, no, I'm not giving away the entire answer because I want you guys to think about it. At least a little bit. Alright, question number 3. What is the base 10 representation of the value represented by the following base 2 number? In other words, this is a base 2 number, and I'm asking you what is the base 10 representation of that. So this we have talked about already when we talked about currency conversion thing. Remember, we said, the current American denomination system is really awkward and is really not user friendly. But if we change it to base 2, everything, makes sense a whole lot more. Remember that discussion? That is what you need to find out what is the value represented by 101.111 in base 2. And then we move on to question number 4. So question number 4 is related to question number 3. We start off with a particular value, in this case 11.766, that is in base 10. What is the binary number that represents a value that is closest to v? Okay, so the key word here is closest, which means that binary number may be larger than, it can also be less than this particular value here, but I'm looking for the one that is the closest. The format of the binary number needs to be like this. In other words, you have 5 digits to the left hand side of the point and 3 digits to the right hand side of the point. Okay, so this is the format of the binary number, and that binary number needs to be closest to this base 10 value over here. Okay, so Andrew typed, in this case, he's not using Boolean algebra. That is correct. I'm not using Boolean algebra. So with this particular lab, we are talking about math. So there's no Boolean expression used in this particular lab. Very good. These are adjacent digits with a decimal point between them. That is correct. So it is the normal interpretation of what a decimal point should do. All right. And then we got a few questions. All right, so getting back to question number 4, I just want to explain question number 4 just a little bit more. If this is the change that you have to give to somebody, okay, it's $11.766, okay, but you're using the currency using the base 2 denomination. The question is how many eighths, how many quarters, how many halves, how many units, how many twos, how many fours, how many eights, and how many sixteens do you need to come as close as possible to 11.766? That is what question number 4 is asking. All right, so now Colin makes a point. The base 2 value in base 3 was signed. I'm a little confused by the leading 0. No, it is not signed. It is simply because, in certain versions of the question, there are numbers with a 1 in this place, and this specific version just has a 0 for that place. Because these values are somewhat randomized, which is a lot of fun. So when you can redo this lab as many times as you want, but each time it might give you different values, which basically means if you want extra practice, after you get all the points already, you can keep doing it until the end of tonight's lab, which is 9:50 p.m. Yes, I remember 9:50, not 10:50. Yes, I have to rub that in. Depends on what time zone then. There's always Hawaiian time. No, we're talking about Sacramento time zone. All right. Well, I know what I said, and YouTube recorded what I said, so I don't have to say anymore. Thank you, YouTube. Thank you. All right, so that's it. Okay, so question 5 to question 8 are basically repetitions of question 1 to 4. So if you know how to solve questions 1 to 4, you also know how to solve questions 5 to 8. All right. Alrighty. So we got everything out here. So I just have to release the lab at this point. And you're going to need to pay attention because the access code is going to be disclosed. Alright, so floating point 1. And oh, you mean Lunar New Year? Maybe, I don't do much celebration anyway, so. Well, Zoe is hungry because in Lunar New Year we typically have a lot of special food, just for celebration of the New Year. So that is why. So Fab 11 950. There we go. And then the access code is double. Okay, I'm gonna type it in. Oh, okay. Thank you, Aaron. You beat me to it. And it is going to keep the highest grade, which means if you don't get all the points the first time, it's okay. Just kind of do it again and try to figure out what you got wrong the first time. And let me click save and publish, so this way all of you can access it. All right, so it is released, and I'm just looking at the number of people on Google Meet. It would appear that we only have 47 people on Google Meet, which is kind of interesting because the class is supposed to have 60 plus people. So some people are gonna watch it, I guess, from now and then hopefully have enough time to get it done. All right. Yep. Some people could be watching on YouTube, and let me look on YouTube here. Yeah, so on YouTube there are 20 something people. Yep, so that will make up for the total number of people in the class. Yeah, I just personally do not recommend YouTube because it lags a little bit more than even Google Meet. All right. Yeah, so Ronald, if you don't mind the lag, it's okay. It's just that the lag on YouTube is pretty bad. Okay, all right. Well, it's up to you guys. I mean, either way is fine. Cool. All right. Well, I share the calendar. I mean, the calendar, you can integrate, my Google Calendar, into your Google Calendar, and then it would even remind you it's time for class, right? I mean, that's the whole idea of doing that. And it's the same link also. You can just, make a bookmark and then just use the same bookmark in the next class. Alrighty. So looks like we are done for the lecture part. So I'm gonna stop the live stream on Google Meet and also on Discord, and then I'll go off, for about 10 minutes. Get a few bites, get something to drink, and then I'll be back to answer questions and practice my Discord foo.
Before you go, did you already go over
So say that
anything
again.
from the lab? Did you already go over anything from the lab? I just had a question for one of them.
Sure. Let's go back to the lab. And which question?
No, the previous lab, not this one.
Oh, the previous one. The previous one. The previous.
I just had a problem with one of the specific problems.
Okay, so let's go back to the previous one. And the previous one would be carry look ahead part 2, right?
No, subtraction and
Oh, subtraction and compare. There we go. Okay.
Yeah.
All right, so let me go to preview. And do you remember the question number?
For me it was question 2.
Question 2? Yeah, the question 2 is always the same type of question, even though the constants may be different.
Okay. Gotcha.
All right, so it's this one, right? Okay. So let me just write down the numbers on the side so I can show the calculation. So we have 0, 1, 1, 0, which is 6, and then we have 1, 1, 0, 0, which is a 12, or -4, depending on how we want to interpret. So I'm gonna switch over to the tablet so I can show you how to do the binary subtraction. Alright, so we have 0 minus 0 is a 0, 0 minus 0 is a 0, and neither contributes a borrow of 1, so we have a borrow of 0 here. 1 minus 0 is a 1, 1 minus 0 is a 1, and neither contributes a borrow of 1. 1 minus 1 is a 0, 0 minus 0 is a 0, neither contributes a borrow of 1. 0 minus 1 is a 1, 1 minus 0 is a 1, and because we have a 0 minus 1 here, we have an overall borrow of 1. So is that okay? Just the subtraction part?
Yeah, that's good.
Okay, so now we want to identify the sign of the minuend. So ms, which is the sign of the minuend, is this guy here. The sign of the subtrahend is this one over here. And then the sign of the difference, ds, is this guy over here. Is that okay? Just identifying the bits that we need in the formula. Are we good?
Yep.
Okay. So now the overflow. Okay, I'm gonna use boldface O here for the overflow. Excuse me. Is ms not ss not ds, or not ms ss ds. Excuse me. So now we just need to plug the values in, right? So we have 0, 1, 1, and then 0, 1, 1. But now we have to remember remember the negation. This one has a negation, so the 1 becomes a 0. This one also has a negation, the 1 becomes a 0. So now we have 0 and 0 and 0. So this entire side becomes a 0. On the other side, we have this one is negated, so the 0 becomes a 1. These two are not negated, so we have 1 and 1 and 1. So this entire side becomes a 1. So now we have 0 or 1, which means the overall value is a 1. And that's the answer. It's asking what is the overflow flag value in this question. So is that working out? Okay.
Yeah, that's fine.
Okay. Yeah, so the tricky part is to remember, what looks like a multiplication is not a multiplication. Although, I have to say confusingly, that in this case, if you look at multiplication as multiplication and addition as addition, it still works out. So that's awfully confusing, but these are supposed to be Boolean operations. So we have and, or, and also the negation not. All right, so we got two more people typing. I'm gonna wait until they're done before I terminate the live stream. Yes, so if m is representing the number of bits in the subtraction, then dm minus 1 is the most significant bit, which is also known as the sign flag, the sign bit. All right. Okay, sure. I'm just trying to answer Aaron's question. What time I started to talk about the lecture? You mean the previous lecture or this one? Oh, you mean the lab? No, I do not remember. I believe it was about 10 minutes before 6:50, so tried around 6:40. I think around 6:40, 6:43 maybe, I started to talk about the lab. Alright, so let's see what other questions I'm getting. Yeah, I think it's about 6:43 because, maybe 6:40-ish. Yeah. we did not actually go over floating point stuff, but in today's lecture I went over the scientific notation. So the scientific notation and also understanding the log stuff is a starting point to understand binary floating point numbers. So it does lead to floating point numbers that we'll start to talk about next Tuesday. So tonight's lab is basically prep work, just to get you guys to think about all the math concepts related to the understanding of the scientific notation, because a floating point number is essentially a scientific notation, but in base 2. So so that's why it is important for us to remember what is the scientific notation and how to solve certain things, involving changing the base. Basically, all the log and exponent stuff. So that's going to be useful. All right. So it looks like we are done with all the live interaction. So I'm going to stop live stream and I'm going to walk away for a few minutes. Then I'll be back and start to answer questions related to the lab. And if I don't talk to you again, have a nice weekend. It is a long weekend because I think Friday and Monday are both off. So go ahead and have a nice weekend and happy Lunar New Year if that is what you celebrate. Yeah, Kong Hee Fat Choi, right? You mean that's the traditional thing to say, which is basically to say, uh, make a lot of money.